Hello, everyone. This is Mike Shou from National University of Singapore. So we made this tutorial video to hopefully make it easier for you to get into this exciting field of video diffusion models. Many thanks to my PhD student, Mr. Yang and Mr. Wu, for helping with these slides. And actually, you can download the slides PDF at this link, or you can just scan the QR code to get the link. So let's get started. So probably you know, over the past 1 or 2 years, a lot of things happen in this exciting field of video diffusion models. Even for just the model listed on this timeline, which are foundation models or base models, there are quite a lot of them from different companies, from different research institutes, universities. But the very first one was actually just released in last year, April, from Google, in short as VDM. And not only for research field, even for real-world applications, there are already quite a lot of successful startups around this field, like Gen 2 from Runway or Pika Labs. So basically, the product or the feature is that you provide a short textual description, and then we will correspondingly generate that video describing corresponding to the textual description. And there are many, many more successful, interesting, promising products. So for this tutorial, we are mainly trying to focus on 2 topics. So the first topic is about video generation. Essentially, given the text, then we generate the video corresponding to that text. And then the second topic is more spatial category of video generation, which is video editing. So in the sense of that, you have basically the user provided a video for the AI to edit, to modify according to the user's description or commands or guidance. So the main difference is that for video generation, we don't have a predefined or provided video. But for video editing, you have a specific video we want to work on. But before diving into these 2 areas, we are going to first recap some fundamentals of the diffusion models. But since this is not a tutorial video for diffusion models, so this is gonna be quick and brief. But the hope is that even for those of you who do not have much background on fundamentals of diffusion models, after watching this maybe 15 minutes long review, you will be able to understand the rest of the content, rest of the video, generation related parts. Okay, so let's get started with the fundamentals. Diffusion models are the perhaps the you heard of this DDPM, denoising diffusion probabilistic models. So that's one of the most famous diffusion models. So the process is essentially consists of a forward pass, which is also essentially the diffusion process, and then the reverse process, which is the denoise process. So you can see actually from this diagram, the provided image is look like this, and then in the forward pass, we kind of like gradually add some noise onto the image, and then it becomes something like totally noise. And then the reverse problem is gradually remove the noise or denoise, and then recover the input image. So that's why it's called denoise process. So researchers found out that, okay, they could actually use this equation to define the amount of noise to be added on the image at each time step and how they are going to be added. So it's pretty much defined by this equation, given this xt minus 1, basically the previous image, and then how we would be able to get the next image xt, how to add the noise, is defined by this equation. And it essentially samples some random Gaussian noise and add on to the image. And then for this equation, it's about t minus 1 to t, so just 1 step forward. And after some mathematical duration, you would be able to find out that okay, we can directly go from, for example, x0 to xt. This can be also well defined by this equation. And for the reverse process, so the idea is that we are going to remove the noise. And how we are going to remove the noise is that we define or we train a neural network to predict the noise and then remove it from the image. So more precisely, this is what does the denoiser look like. At some time step, for example, step T, during training, we know what does this FT looks like, and then the task is to fully recover the original image actually. So the thing we want the noisy predictor to predict is the noise on this XT image. And once the noise has been predicted, then we can remove basically minus, as indicated by this minus sign here. We remove this noise from the original image to recover to basically get the original image, which is our training objective. And one thing to note is that there's some other conditions in the noise predictor network, like the time step T, it controls, okay, what kind of amount you wanted to remove, I mean, in terms of the noise, and also the condition, because in this case, it's a so-called conditional generation. We wanted to recover the original, image as a cat, so we provided this textual description as well as the input or as the condition for the noise predictor network. But the important thing is that the xt and x0, so it's directly from t to 0. So it's a so-called one-step prediction. We want basically when during training, we just directly trying to remove the noise. But during the reverse process, when we try to use this then denoiser to recover the original image, like from xt to the original image, we actually do it not just one step, we do it step by step. So this is a bit weird, but you can consider or understand it like maybe the denoise process is not that perfect, it will make some errors, and then we wanted to add on some additional noise, and then so on and so forth through this iterative process, then we can gradually recover the more precise original image. So each time step only sort of remove just a small amount of noises. So more precisely, what it does is that after minus the noise predicted by the noise predictor network, we further randomly sample some Gaussian noise to add on to the output. So this would, what does it looks like from xt to xt minus 1. So DDPM denoiser is like step by step. So it step by step go from xt to xt minus 1, so on and so forth, and then go to x0. And typically in practice, it would require a few hundred steps to complete for generating just one single image. So you can imagine it's definitely not that ideal. It could take a lot of time. So can we speed up? Basically, can we skip some steps during the denoising process? So of course, it comes with the another very famous diffusion models, which is called DDIMs. So DDIM, the idea is that now we do not randomly sample another noise during the generation process. We do not randomly sample another noise, but instead we directly use the noise predicted by the predictor network denoiser. We use this noise. So firstly, we minus this noise following this equation, and then we add on this noise again. So if you compare these two different models or different sampling process, is essentially DDPN, it cannot be 10 steps, and it usually requires a few hundred steps to generate an image. And And during each time step, we sample noise to add on. But for DDIM, it's pretty fast. I mean, still has room for improvement. And nowadays there are new technologies to improve its speed, but it's already faster than DDPM and it requires only 50 steps to generate a reasonably good image. And also, it does not randomly sample noise during generation, just use the noise predicted by the noise predictor. And because of that, for DDIM, we can do something so-called inversion. Okay, so inversion is not a new term in diffusion. People use that in GAN as well. So the task of inversion is that, the typical inference or generation process is that given noise throughout the denoiser, we denoise noise and then denoise the image and then recover the original image. So the inversion is basically the inverse process. It's the process that we provided this original image. And then we also have this chain, this length denoiser. Then we are trying to find out, okay, which initial noise can be actually denoised into this image. So basically, given the predicted image, we found out what is the input. So this is the inversion process or the task of inversion. So you can actually feel like it's similar in terms of the process comparing to the forward diffusion process. In forward diffusion process, we, every time step we add on this random noise. But for DDIM inversion process, the noise is not sampled every time. Instead, at each time step, we can invert the noise. We found out this invert noise, well, basically from the DDIM denoiser, which noise that was predicted by this DDIM denoiser at that certain time step. So that's a pretty quick review of DDIM, DDPM. If you wanted to learn more about these fundamentals, I would highly recommend you to watch these two, this CVPR tutorial about diffusion models, and also this blog is perfect. And there are also other Mandarin materials you can find out. Maybe kind of suggestion is that after watching these fundamentals of theory, you would really like to try it out. Look at the code, implement by yourself, so that you will be able to have a better understanding about its mechanisms and how to actually implement that in practice. So for the, we mentioned this already. Basically, for this texture description is used as a condition basically as input for the noise predictor, so that the image generated will be actually conditioned on this description. But maybe one thing is that this is sequence of words, this is tokens, how we are actually going to fit that into a neural network for processing numbers. So there is a technique from the OpenAI, which is called CLIP. So this model is essentially doing image text matching. Basically, during training, they have a lot of these image text pairs. So for each image, we have a texture description, and they have a lot of these image text pairs. And then they have an image encoder to extract the feature of the image, and a texture encoder to extract the encoding or embedding of feature of the text. And then they can do this kind of matching. They match if these two, like I1, T1, they are corresponding to the same thing, then the similarity they suppose should be high. So this is the training objective, and after training on a lot of data, they would be actually to not only have these two feature extractor, but also the features, the embeddings, they are in the same semantic space, so that they would have like higher similarity if they are corresponding to same image. So essentially, for this conditional, for this condition or texture this condition, we can use this text encoder to extract the features, and the extract feature it would be nice and fit into this denoiser, which is in the sort of like the image domain. Another very interesting is about the so-called latent diffusion. So far, what we have been talking about is like denoising from the original image, add some noise and remove noise. So all this happens so like in the pixel space directly. And sometimes we wanted actually the process to be more efficient. And then people introduced the idea of the latent space. So the idea is that we have another two neural network. One is encoder, another is so-called decoder. So the idea is that we use encoder to extract some high-level latents or embeddings of the image, and then it is still like feature maps, basically a stack of feature maps, and then but they are in the latent space, in the high-level semantic space, and then we do this diffusion, add noise, denoise, only in this green latent space, only operate on the latent, on the features. And after denoise, we have to denoise the features or latents, and then we need to go through this decoder in order to recover the original pixel. So this is actually used in the very famous stable diffusion model. So the process, this is exactly the diagram from the paper. So given the input image X, we go through this encoder to get the latent or embedding Z, and then you will be able to go through the diffusion process and then denoising process. And for the denoising process, after going through the denoising process, we have the decoder to decode the latents into the pixel space original image. And also for stable diffusion, they use a lot of different conditions. I mean, they would be able to use a lot of different conditions, like not only the text description like a cat, but also they can use condition like image. So these are useful for the case of that we want to do some, inpainting or editing, or it could be a semantic map, and then they can generate the realistic image for a given provided semantic map. So here are some examples of the images generated by stable diffusion. It was pretty good. And they have different, it has been improved over the past years, and new version have been released, like the recent SDXL can basically generate very high resolution, high quality images. Another technology I'd like to introduce is about this LoRa, in short for low rank adaptation. So this is actually technique was originally proposed in the efficient fine-tuning domain. It's not was designed for diffusion model. It's actually more generic. So why this is popular is because, for example, the stable diffusion model is great, but it cannot generate some specific domain images. For example, this kind of cartoon image. But different, users, people, they have different domain-specific data. They would like to fine-tune a little bit about the original diffusion model to customize it to a specific domain. And what they did is that they used this LoRa technology, and the idea is that, this is diagram from the paper. So essentially, this is input X and output H, and the original stable diffusion model weights, they are fixed. They are pre-trained. Basically, the pre-trained weights are fixed, and we only need to train additional string, and this string has only very limited amount of parameters too. So that's why it's parameter efficient. And then you add up the output of these two strings. The idea is looks like that. And in the community, this was quite popular because they can further train their own LoRa and then release to the public for other people to use. Another technology people have developed is this so-called Dream Boost. So it's also fine-tune the is also trying to fine-tune the diffusion model. But what is different is that they don't fix. For LoRa, it fixes the whole base model, diffusion model, or whatever other base model. But for GenBoost, it actually need to turn the UNet. So the idea is that we provide a few images for a specific concept, like this pink bag. Then you would be able to generate it in other different kind of scenarios. So what they did is that they used this, like provided a few examples, a few example images as the input, and then trying to learn a row token, for example, V, to represent this specific concept. But the original model would not be able to recognize or understand how to map this V to this specific dog or specific bag. So they need to fine-tune this diffusion model in order to make it be able to react correctly corresponding to this row token. So then another technology is there about maybe you have heard of that already, control net, which is quite famous in the sense of that it can provide very precise user control into in terms of what kind of thing you want to generate it. So like the user can provide or this like canny age figure, and then the generated image would very much align in terms of age with the this like age figure. And also you can have other conditions like human pose. So then the generated people always have this kind of a pose. So how they did that is also have this like fixed and trainable part. What they did is that for the original stable diffusion, they make a copy. And then only train this copied part. And for this copied part, they have this like additional condition. For example, the age map or human pose map as the input. And they would fuse the output of this like copy part and also the original stable diffusion. And they can handle a variety of different conditions, like the sketch, like the depth map, so on and so forth. All right, so just a quick review of the fundamentals of diffusion models. And now let's get into the main part of the video generation. So these are, we see this diagram before, these are all the, I mean, maybe incomplete, sorry, due to the short timeline, maybe we missed out something. But there are quite a lot of basically video foundation model or base model for diffusion-based generation, video generation. So we sort of like organize these models and also other related technologies into 7 categories. So the first 3 categories are more about these foundation models of base models, and then we introduce other related topics in this field as well. So let's start with the very initial pioneering works, like the one VDM from Google and other works like image and video from Google as well, and Align Your Latent from NVIDIA, make a video from Meta. So again, the task is about for, the so-called T2I is about from text to image generation, you generate an image. But for video generation is so-called T2V. From a texture description, from a texture prompt, we generate a video. So what is the difference? Very straightforward. The difference is that the output for T2I is 2D image, but for video generation is 3D. And for 3D is in the sense of basically just a sequence of images. For example, maybe 16 frames of 2D images. So how to handle this basically change from 2D generation, 2D output to 3D output it's a new topic or new challenge in the diffusion field, but for more general video understanding for the video field, it's not new. People have been dealing with this problem for several years already. Like for action recognition, previously we had model for image recognition, and now how to turn it to recognize action in a video. So people, in that case, people started this problem already. So back then in ICCV 2015, researchers had developed this like convolution layer, which is so-called 3D convolution. So the idea is that for 2D convolution, given the input image x h by w, we have a 2D kernel k by k slide over this input image, and then you generate 2D output. For 3D convolution, is essentially, so for the input, you have another dimension L corresponding to the time or the number of frames. And then for the kernel, convolutional kernel, it also has 3 dimensions, k by k by d. And we slide over this kernel over h, w, and also L as well. And so that the output will be of this 3D. So this is quite effective, but later on, people want to improve its efficiency because we know this like T by D 3-dimensional kernel is quite computational expensive. And then people come up with this smart idea of the so-called 2+1D. So 2+1D is that for each specific layer, we factorize into a 2D spatial convolution followed by 1D temporal convolution. Okay, 2D spatial convolution and 1D temporal. This one operates only on the, spatial, and this one only operate concerns about the temporal. And people found out this one can achieve good performance and is more efficient. So now let's talk about this very initial pioneering work of the video diffusion model from Google, and this is the 16-frame fireworks video generated by itself. So how they make this happen is exactly about extend the 2D diffusion model to 3D. And they use the idea of the so-called factorization as well. Factorize the 3D unit over space and time. But actually, what they did is not like the complete 2+1D convolution. It's actually just the 2 in the 2+1. So it's more like a per frame model, or what they call space-only 3D convolution. So basically, they have for the the image 2D convolution, it can be extended into this kind of like space-only per frame model by just adding one more dimension, and along this dimension, the kernel size is just 1. So originally it was 3 by 3, now it's 1 by 3 by 3. So it actually this 1 corresponding to the frame, and over the only temporal dimension is actually just process each frame independently. But besides the convolution layers, we also have the temporal layers. For the spatial temporal layers, they remain same as the image diffusion models. But for the we still want to model some sort of temporal, right? That's very important for video generation. So they insert these temporal attention layers. So the temporal attention layers, you can think of that is basically perform the self-attention or cross-attention, these kind of operations over only the temporal dimension. So for every pixel, they are considered, or maybe you can kind of like merge them into the batch category. And the self-attention is performed, is measuring the attention basically between, for example, a specific, for a specific pixel, and how the specific position pixel changes over time. And if there are 16 frames and this self-attention or cross-attention operations happens only between these 16 values. And then we are going to actually explain more in detail about this, like how to build out this kind of like video diffusion models by using the one from Meta, which is called Make a Video, because it's kind of like it has a diagram, or this paradigm that is more commonly used nowadays. So this paradigm is essentially of a cascade process. basically video generation is so difficult, so we don't want, or we probably not want to generate in just one single step, like the this one unit. Perhaps we can do it that step. So provided this input text, we actually have in this make a video, they have 4 steps, 4 stages. So the first stage is about the so-called spatial temporal decoder. So it basically from the noises, we decode or generate these like some keyframes, and they are of pretty small resolution, and the frame rate, the number of frames we have, is also not that many. And then we first wanted to, interpolate to increase the duration, the number of frames. So we do this frame interpolation. Given this like 3 frames as input, and we provided some masked out, maybe like noises. But the idea is that then you can fill in this gap and to generate the frames in between. And after that, the duration increase, but the spatial resolution is still not high. So we have a spatial temporal super resolution module. It improves the basically resolution, like the visual quality. And so, and then after that, we have even further another spatial super resolution to further increase the resolution to make it of higher quality. So more specifically, we can see that after the spatial temporal decoder, the size is 64 by 64 of 16 frames. After the frame interpolation, it increased to 76 frames, but the size is still 64 by 64. And then after the super resolution module, it increased to 256 by 256. And further on, it can reach 700 by 700 something. So so this is the so-called cascade generation paradigm. So more specifically, it also, for video generation, it also designs this like temporal operations like convolution or attention layers. So let's talk more about this kind of details. So for this make a video one, it actually follows the 2+1D paradigm. For the convolution layers, so it's used it first start with the 2D convolution, only do the convolution on the basically image-wise, and then followed by 1D temporal convolution. One thing to note is that for spatial convolution, they initialize the 2D count by the pre-chain T2I weights, text to image weights. So typically, actually, for all this kind of like work later, including those we will introduce later, people would first train a T2I image model, and then use the image model as initialization when train the video model. It makes sense because image model already learns about the appearance, etc. So why not start with the image model? Okay, so that's the temporal convolution, and another operation is about attention. So for spatial attention, still it's the same and same as the T2I weights, And given this input data, so this is the spatial Y, this is spatial Y. So we do the and this is the temporal, time-wise, and we do at each time step. We do the silver attention or other attentions, but basically spatial attentions within basically this kind of like an image, and then followed by temporal attention layer. It will perform this like 1D attention across this dimension. Basically, for this specific position, it has different values over time, and we do the attention across this line. And for another position, we also again do this kind of like 1D silver attention. And more specifically about the training process, we have 4 networks in this process. One spatial temporal decoder, 1 interpolation module, and 2 super resolution module. So all of them actually first train on the image only, so they provide a good initialization. And then we insert the temporal layers like temporal count and temporal self-attention, and we insert these temporal layers and then fine-tune them on the videos. So the fine-tuned alternate dataset is this so-called WebV 10 million. It's a pretty good dataset, and also another 10 million subset from the HD VNLA 100 million dataset. So the WebV dataset is dataset provided by this IGCV paper. So the essentially is it consists of video caption pairs, and the video is typically of pretty good high quality, and you have the texture description accompanied with that. So talk about the dataset. Once we train the model, we want to evaluate it. And in terms of evaluation metrics, there are quite a lot of metrics used in this field. But most of them are the so-called automatic metric, basically something we can compute automatically. But as always, like in the image domain as well, the automatic metrics always may not be that perfect. And human ratings, human score, basically ask the human to compare which two videos, like given these two videos, which one is better. Always like human score is more reliable. So people always also do human evaluation, but it's costly and time consuming. So there are something in between, like a hybrid way. And this, because it's a hybrid matches, they essentially still do automatic computation to get out a lot of different scores. And then they are trying to manipulate these scores to approximate the human ratings to make it basically the automatic computer score as similar as the humans' opinion, humans' behavior. So we will first introduce these different automatic metrics first. And they can be categorized actually into in terms of the image and in terms of the video. So this also may not be that complete, but I believe after this you will get a sense of like different kind of metrics. So the first one is FID. So the FID is essentially measuring the difference between two distributions, the distance between these two distributions. So for these red dots, they are corresponding to the real images, and for the green dots, they are for the generated images. So they are operating in the feature space, which is from the Inception V3 model. So the idea is that given input image, it can be real image or image generated by your model, and then we will use this CNN to extract its feature. So for a specific category, for example, this of cat or whatever, and then you can have a reference set of the real world images for this category, and also a reference set for this set of this generated images for this specific category, for example, cat or kid. And then we can measure, as long as these two distributions are very close, then that means the images you generated are more realistic, better. So this, after go through this neural network, we can actually, see that this pretty high level already. It lose some details at the pixel level. So there are also metrics that more focus on the pixel level similarity. And this is the so-called PSNR, and you can see that it actually directly measures the pixel difference. And there are also other metrics, which is so-called SSIN. It takes into account different functions, and then the output will be a combination of different functions. And the different function corresponding to measuring the or comparing the luminance, contrast, etc. Another pretty good metric people use is actually just use clip. So we mentioned that clip is actually designed to measure the similarity between or trying to match the corresponding text and image. So for the provided category or provided texture description, if the generated image is well aligned with this text, then supposedly they will have a higher similarity score, right? So that's why clip can be also used for measuring the image text similarity used for basically evaluating the performance of the generated image. So we fit generated image into the image encoder and see how good is the similarity. So that's for image, and naturally for video, we can extend the FID to FVD. So given the input video, we can use a video network, like for example, 3D convolutional network, train on some standard dataset connect is 400, and then you can extract the features using this 3D conv. And for measuring the distance between these two distributions, people have also other ways like this MFD as well. So there are another metric which we call inception score. It can be used actually in image as well, not only just for video, but we do have this inception score. So the idea is it can measure two things at the same time, which are video quality and the generation diversity. Because we don't want always, when we ask to generate a cat, it's always the same cat. We want actually every time maybe they look like different. And more specifically, what they done is they have these two distribution measure, and this IS is essentially measuring the KL divergence between these two distribution. So the first one is this probability of Y, which has no condition. So essentially, kind of like just ask the model to randomly generate something. So if and after generation, we could do, for example, classification to determine the class of the generated image. And if the generated images, they kind of like uniformly fall into different categories, so that means your generated images are of very good diversity, right, in terms of sampling different classes. But when we have some condition, for example, the condition, when we have some conditions, for example, hand, then the generated images you want it can only be categorized or classified as hand. So that means the generated image is correct, it's precisely reflecting the condition, right? So that reflects the quality. So this KL divergence measuring these two distributions, and typically a larger IS score, that means basically a generated distribution is a shaper and more distinct collection of images. And also clip can be used for video as well. And more specifically, how we use that is that it can be used in terms of measuring the frame temporal semantic consistency. Because what is the difference between image generation and video generation? So video is something that sequences of image, but these images, they are consistent over time and they move like smoothly. So how consistent are these images over time is a very important dimension that we should look into. For example, my hair is maybe black now, and in the next frame, I don't want it to be kind of yellow or red, right? So how to make the consistent, how good is consistency can be computed using the clip score as well. So we extract basically clip embedding, image embedding for all frames, and then you average the report the similarity between all pairs of frames. So this only concentrate on only use the image embeddings and then look into the similarity between different images embedding. Okay, so those are the very quick review of all the metrics. And always, we still rely on human ratings. Like for example, in this mega video paper, they design these comparisons, compare the video generated by mega video versus other models like the VDM from Google or the Coq video, which is not diffusion based. And they ask the human basically to rate, okay, which one do you prefer? And they actually it can be, I mean, when you ask the user, ask the annotators about this question, we can ask about different dimensions. We can examine different dimensions. For example, quality. Which one maybe has higher quality, higher resolution, more realistic? And also another dimension to look into is the faithfulness, right? This is very important. We don't only want video that looks very great, but does not really precisely capture the content described by the text. So how it can correctly reflect the texture, the content, the scenes described by the text, we also wanted to consider that as another dimension. And for the hybrid metric, so one of them is from this paper, so-called EVA crafted. So the idea is that you design prompt list for evaluation, and then so on and so forth. You will be able to actually get 18 metrics, which each of them corresponding to different aspects. For example, the visual quality, the content quality. But the idea is that they wanted to mix that to fuse all these metrics into one score that approximates humans' rating. And how we fuse or average these different scores is basically weighted sum. Right? So when it comes with weighted sums, then we have the coefficients to emphasize some matches and maybe don't pay that much attention to some matches that matter less. So it's a regression problem essentially. So we regress the coefficients to hopefully to generate an overall score that will align with users' opinion. So these are all the metrics I wanted to introduce. And finally, for this makeup video, it used some of these like automatic metrics as well. And for example, the FID, and comparing to the previous method, it has basically better performance. And also it compared the clip similarity as well. And also the test on this UCF data set, which are, I mean, in the era of GAN, people use or this UCF as benchmark for quite a lot of times. But I think for diffusion models nowadays, we rely less on this UCF video data set. I think it's a good sign in the sense of that the field progress so fast. And now the video we can generate even higher, better quality than the video in the UCF data set, which was maybe was a data set collected more than 10 years ago, I think. And also they did human evaluation as well. And here are some examples of the videos they generated. And it was quite interesting still now. And they can, because it has this interpolation module. So if you provide, for example, 2 images, it actually can fill in the gap to fill in to imagine basically how it will transit from the first frame to the next frame and to generate a video looks like that. So that's for the makeup video from Meta. And yeah, from different companies, they all have their own, video diffusion models. Even for Google themselves, they have another image, video diffusion models. So this video diffusion model is called actually image gen. So you can see it's very interesting that it has this image in this term of image in this video model. So why is that? Is because it's actually built upon their image diffusion model, which is called image gen. So image gen is already a cascade generation model. It's already a cascade generation model, even for image. So given a task, they have the text to image diffusion model to generate an image of 64 by 64 size. And then they have super resolution module to increase to 256 by 256, and then one more super resolution to 1000 by 1000. So it's great. It's already cascade. And for the image and video, it basically extends some, as always, the 2D convolution into 3D convolution, attention layers from spatial attention to maybe spatial temporal attention, or maybe add some temporal attention layers, so on and so forth. So and for some super resolution, they also have the temporal super resolution, etc. So the idea would be quite actually common in the high level. And for NVIDIA, they also have this align or latent high resolution video synthesized with latent diffusion models. So one thing differs from the works in Google or the Meta ones is that for this NVIDIA work, they built upon the stable diffusion. Actually, I mean, not so the idea is that more precisely is actually built upon this latent diffusion models. So it's more efficient because latent diffusion models, they operate in the latent space instead of directly work in the pixel space. So it's basically more efficient. But because of that, they not only need to do this keyframe generation, interpolation, super resolution, but also they have this kind of decoder. They have this decoder to decode the latents into the pixel space. They need to have this additional module of decode from the latent to the pixel space. And then the upsampling module actually happens after the decoding. Okay, so in terms of the how to make it from 2D to 3D, right? So similarly, in high-level idea, for the latent space diffusion model, they will insert temporal convolutional layers and the 3D convolutional layers. And for the decoder, they add some 3D convolutional layers. And for the upsampling module, it's a diffusion-based module, and they add 3 convolution layers. Okay, so all these are great works from these big companies, but maybe the thing is that they are not open source, so they cannot be used by community, by our research field, right? So that's why a lot of us actually working on developing our own base model, foundation models, and make it open source for other people to use. So there are quite a lot of work in this open source domain as well. For example, Shou one from our own group, and the Video Crafter Stable Video Diffusion, which was released just recently, and the very good model scope. So we start with the model scope T2V. T2V means the text to video, right? So the idea is that, again, as similar as the closed source work, we also wanted to start with the pre-trained image model. So we leverage pre-trained text to image model for video generation. And the idea is that we inflate the stable diffusion to be a 3D model, but you preserve the pre-trained weight. So again, similar logic with the previous the works we have introduced so far. So how they did that is that they insert this spatial temporal blocks is essentially again a 2+1D framework, 2D CN in the spatial and 1D CN in the temporal. And for the attention layers, similarly, they have 2D attention in space and 1D attention in the time. One thing to note is that, or interesting about this work is that they can handle a very number of frames. It's because for the temporal layers, both the convolution and the attention layers, they can actually set it to be designed, set to be the it's actually a variable length. So variable in the sense of that why we want it to be variable is because it can be set to be 1 in some cases. So if you set the temporal length to be 1, then it's essentially reduced to be kind of like a image generation model. So with that, they can train basically train on both like image and the videos. And on the some standard benchmark like the MSR-VDD dataset, we can see that it achieves a pretty good performance, comparable, even better in some cases than the makeup video. So this is the so-called model scope, and later on, people also released this zero scope model. What it does is that it fine-tunes model scope on a small set of high-quality videos. If I remember correctly, it's about 10K videos, but it's of higher quality, higher resolution, like 1000 by 500 something. And for the model scope, it has this kind of like watermark in the video generated. but because it's trained on the WebView dataset, and the WebView dataset it has the Shutterstock watermark. But after this like fine tuning on just a small of data, it can remove this like watermark as well. So these two models have been used quite a lot by the community, and here are some basically visual examples. So models Go or Zero School, they are great. They are very good open source models. But one thing we notice is that video text alignment is not that perfect, in the sense of that sometimes the video generated cannot correctly reflect the content described by the text. So for example, in this example, a panda besides the waterfall is holding a sign that says Shou. So for the result generated by Zero School model scope, it does not contain Shou. And even for commercial works like Gen 2 cannot. And for another example, like a blue tiger in the grass in the sunshine surrounded by butterflies. So we can see that actually for Zero School, model school, or even Gen 2, they cannot generate video of butterflies. So that means when the text becomes a little bit more complicated, in contrast to previously maybe the text prompt is only a few words like person is running, panda is jumping, something like very simple. But when the text becomes a little bit complicated, then it becomes kind of challenging to generate the content precisely. So this motivates us to develop this work from so-called Shou one. So it has much better text to video alignment. So the idea is that we found that we look into the reason basically why this kind of like model, Zero School models, so they cannot generate or content that precisely align with the text, but some models like the image and video, they can indeed actually generate pretty precise content. The difference there about the diffusion models, whether it's in the pixel space or whether in the latent space. So again, let's take a look at this diagram again. In the pixel space, the model for the model in the pixel space, it directly interacts with the image and pixels, so that it can have better control over the content to be generated. But for the model in the latent space, although it's much more efficient, but goes through this encoder-decoder thing, the content, especially the texture contents, they cannot be reflected correctly on the generated images or videos. So here is also basically a toy exploration that we did that compare the pixel model, latent model in terms of generated videos for this sentence. And we can see when we look at the just a very small video, these are keyframe size video generation. For pixel model, it already, because the size is small, but it can already capture the content like blue tiger, sunshine, butterflies. But for latent models, it cannot. And it's not because the size is too small. When we increase the size, for example, use a larger size latent model, it cannot capture the content as neither. But so then why we just use the pixel model, since pixel model is so powerful. But the issue or challenge is that pixel-based VDM takes much larger memory than latent-based VDM. So for example, because as always we have this like cascaded as different stages, right? So in the keyframe stages, if we generate, if for generation we use pixel model, and for the super resolution module we also use pixel, always use pixel model. Then the maximum memory you would need is like around, for example, 70 gigabytes. But when we actually switch to, for example, latent, then you can see the memory is just 15 gigabytes something. So something sweet is that in the small size, low resolution key frame generation part, if we still use pixel, but in the later stage, when we work with larger resolution, in the super resolution part, we use latent, because we care about the efficiency when the scene really becomes larger. And we found that the memory actually consumption is actually comparable with all latent models. It's 15 gigabyte something. But in terms of the text to video alignment, it's actually much better than the latent model. So this is basically text to video alignment, and we ask human annotators to compare the videos generated by the last three columns, last three rows. So even we just use this pixel model in the low resolution part, it can preserve in the final video, it can preserve the good text to video alignment. So with that, we come up with this Shou model, which in the first stages of keyframe generation, frame interpolation, super resolution, because it all work in the low resolution and we feel like we are affordable in that case, then we use pixel-based diffusion models. But when the resolution is already high and we want to make it even higher, in the final super resolution module, we decided to use latent-based diffusion to do that. So it's mixed, it's a hybrid pixel and latent diffusion model. So with this kind of memory efficient way, we can generate this kind of videos. So in this demo video, it's actually a sentence and then we generate a few seconds long video clip for that, and we mix up them, concatenate them together. And you can see actually for this model, it has better text to video alignment, and more specifically, like in this example, the motion is quite large. So it has the capability to synthesize large motion. For many commercial products nowadays that are open source video diffusion model, their motion not that significant, and our model would be able to synthesize the kind of large motion and in a memory efficient manner. Okay. And there are also other open source models I'd like to briefly touch on. For example, the video crafter model from Tencent. Similarly, it is essentially to insert some temporal layers into the latent diffusion model. And also we have this LaVi model from NTU, which did joint video fine-tuning, and more specifically, it collect or propose or develop a new dataset for training. This like VNMEO 25 million. It is of basically higher quality, and with this higher quality dataset, they have better performance, better video generated. So here are some examples of the video generated. You can see the quality, the resolution are much better. So notably, recently, Stability AI released this stable video diffusion, in short SVD. It basically pursued in the similar direction as the LaVi, in the sense of they create a much better training data set and did a lot of work in the sense of in terms of the data processing and annotation. So it has different stats. For example, cut detection and clipping. So they basically do some short change detection, cut detection. So that when we come up with a text description, it would corresponding to just one shot rather than different shot, or maybe shot of scene change. So the text would be able to more precisely correspond or more precisely describe the content in that shot. And then for the texture, how to generate the caption of the video, they actually use a synthetic way. They use the Coca image capture, and also they use WeBelieve to generate video-based caption. So they have different text descriptions and then use LLM, large language model, to summarize them. And also, they would actually compute some kind of similarities and other kind of scores. And also another two technologies I want to maybe emphasize is that they actually run this obviously conduct this like static scene filtering. So the idea is that because as mentioned, one of the issue for video generation nowadays is that the generated video does not have large motion. So one possible reason is that the training video lack motion. So why not we just remove in the training data, remove videos that does not have, do not have much significant motion. So they did that by compute the optical flow magnitude and filter out the static videos. And also they do text or OCR detection to remove clips that with a lot of text in them. Especially like in actually WebV data set, they have a lot of videos that just the text. So this is a bit depending on your use case. So if in your use case you do not want to generate video that has text, maybe you can do that. But if you do want to generate a video of a lot of text, maybe you can keep that in your data. But anyway, they collect a very large data set of LVD, so-called LVD, of 500 million videos, clips, and of duration more than 200 years. And they also have a subset, 10 million subset, and the total duration about 3 years. So I guess this is comparable to WebV. This is also of 10 million clips. And they do the filtering, as we just mentioned, they do this kind of filtering. And after filtering, they filter LVD into this part, and this 10 million subset is also further filled into this -F, which has total duration less than 1 year, about 2 million clips. So you can see it's about 25% something. So yeah, it's basically it filters out a lot of videos of not that good quality, and actually quite important in the sense of that you can improve the training efficiency. So more specifically, it has different stages in the training this stable video diffusion model. But maybe as you can imagine, it's always the it's not that much different from the pipeline we have seen so far. So first of all, train an image model. But more actually what they did is just they already have the image model. So they just initialize the model by the stable diffusion 2.1 version. And then we are going to do this stage 2 video training. Before that, we do some inflation to inflate it to be a 3D model. And then once we inflate the 2D model to 3D, then we can train on the video data set. So this like LVD data set we just mentioned about, they are use this data set for pre-training. So it's a pretty massive scale training. And finally, they have another stage, the final stage of high quality fine tuning. So like how we fine tune, model scope to zero scope. Similarly, here they fine tune the base model from stage 2 on a high quality video data set. But unlike in zero scope, we only use 10K videos. Here, this small amount of data it still contain 1 million samples. So these are 1 million very high resolution videos. And they fine tune it for 50K iterations. And so they reach this like 500 by 1000 resolution, in contrast to previously 300 by 500. And also they can further fine tune the model for different application or tasks. For example, image to video generation. So the idea is that to add on some dynamics into the image to make it move, or maybe do frame interpolation. And also they can do interesting to this multi-view generation, in the sense of giving an image, and then we can generate a video that sort of like the camera is moving around the object in the center. So in that sense, although we generate a video, but each frame in the video is corresponding to different view of the specific image. So that's quite interesting. And here are some examples of the stable video diffusion model. And you can see that it's pretty good. All right, so there are still other foundation model or base model, but they are closed source. Like for example, the Pioca, latent shift, video factor, video fusion. All these are pretty good work. All right, so far we have been talking about base model, foundation models, which takes a lot of resources actually for training. So that can only be done by a few groups or a few companies. So people always think about how we can make the training more efficient, right? And come up with some training efficient technologies. So that's what we are going to introduce now. So the first one I'd like to mention about is this animative one. It's a pretty good work in the sense of that. I mean, it's still, although it's called training efficient, but it still requires training on web 10 million data set. So it still requires some kind of large resources for training, but it's efficient in the sense of that it can be used widely by different users in this community. So as we mentioned previously, we have this LoRa or Gene Boost. They are developed by the community for basically adapt the T2I based model into some specific domain. Like for example, generating a cartoon like images. So imagine if we wanted to generate a video for this specific domain, are we going to train our video model specifically from this like personalized, customized T2I model? Like previously when we train the video diffusion models, we always start with a T2I model initialization, always start with an image model as initialization. But if the base model has been changed to, the image model has been changed to some specific other models, do we need to redo this video training again? Hopefully no, right? So the idea is that can we having some general like video model that can be used for all these kind of different T2I image models without specifically fine-tune for like this domain or this domain. So what they propose or did is that, again, in terms of architecture, it's very similar in the sense of how we change from 2D to 3D or video generation. They introduce some of these motion modules or motion layers, motion module, motion layers. And during training, for example, when we use for example, stable diffusion model as the initialization, and then we only need to change this, like motion module layers. But for the base T2I pre-trained weights, they are frozen. For the base image model, they are frozen. So this like gray part, they are fixed. So why we fix that is because later on we can replace them, because we can replace the gray part with maybe this red part. This red part may be corresponding to the specific domain's T2I model, like weights of the personalized T2I model. They are of the same architecture, just fine-tuned a little bit, right? And we'll just in another direction is that you can think of that once this blue part, this motion module has been changed, we can apply or insert or plug in this motion module directly into other image model. And turns out this works pretty well. So for this cartoon T2I model, we can plug in the motion module. For maybe another Disney kind of like personalized T2I model, we can also plug in this motion module. And they can work because they are not that different essentially. I mean, these T2I models, they are not so essentially different. They are fine-tuned from the same stable diffusion model, for example. And more specifically for the design of the motion module, this is the design of the motion module. They have some project layers and also self-attention layers in the middle. For training, they train this motion module still on the WebWeave 10 million dataset. But the good thing is that they resize the 256 by 256, and turns out the experiment shows that it can be actually generalized to higher resolution. That's pretty good attribute in the sense of that we save some computation during training. And here are some results that basically for Jinboost or LoRa, different personalized T2I image models, and we can turn this image model into video models, turn this T2I model into video generation, text to video generation models. Make basically, previously this model can only generate image, but we can now make it move by adding just simply inserting this motion module. So, okay, this is fantastic, but it still requires model training, right? And not that cheap, actually training on WebWeave 10 million. So maybe a more research-oriented question is that, can we just change the stable diffusion model into video generation without any training, without any fine-tuning at all? Can we do that? So if we think about this question, how we can make it happen? Or what is the difference between image generation and video generation? Video generation generates dynamics, and the challenge is that how you can maintain the consistency across different frames. So there could be two principles to make it happen. So the first thing is that recall in the when we talk about the inversion, right? We mentioned that we can invert our image using the noise that we invert into noise. So that noise deterministically can leads into that specific image. So that means although it's a noise, it looks like noise, but it still has some patterns inside. So if for different frames, now we randomly initialize noise, but if we make they share some similar patterns, we make this noise share some similar patterns, then the generated image, they will have basically similar pattern, more similar. Another principle is that we can, during the UNet, we can make the intermediate feature of different frames to be similar. That's, I guess, easier to understand. So for the first principle of the noise, so what we did is that we start with in this work, test to video 0. In this work, test to video 0, they start with noise of similar pattern. Basically, for the first frame, you can still randomly sample, but then later on, how you going to come up with the noise for the rest of frames? They define a global scene motion. For example, for this horse, then maybe they can define a global motion like just move to the left. So they, even at the noise level, they just move the noise a little bit to the left every time, and so that by this kind of translation, we add on some motion into the noise, but the noise they share very similar patterns. And another thing is basically make the intermediate feature of different frames to be similar. And what they did is that in the self-attention layer, in the self-attention layers, they always use K and V from the first frame. They always use K and V from the first frame when they do the self-attention. And there are another optional operation is that to make the background basically more consistent. They do some smoothing. Essentially, the idea is that to generate or extract the mask of the main object, because actually the task of video generation here in this paper is more about generating motion or video for a specific or object-centric video, so that they can generate a mask of the central object, and then you can obtain the background and average them, smooth them. And here are some results of this test to video 0, and you can see it's quite impressive in the sense of that it does not require after no training at all. So without training, it can generate this kind of like videos, so that's already quite impressive. There are also other very good work, like for example, match video, simple diffusion adapter, dual stream diffusion NAND, etc. They are also developing efficient training technologies. All right. So far we have seen quite a few video generated by these diffusion models. They are pretty exciting, but they are pretty much just a few seconds long. And very often the video are not so complicated in the sense of that you have an object in the center of the video. So how about can we generate longer videos that maybe several minutes long? Can we generate more complicated video like at the movie level? Have a lot of different subjects and different scenes, etc. So we'd like to branch out a little bit into this more exciting fields. So the first one I'd like to introduce is so-called about storyboard. So there are quite some works along this line already. What is a storyboard? So essentially the idea is that if I just told you this sentence, two men stand in the airport waiting room and stare at the airplane through window. Okay, after I said this sentence, what is in your mind right now? So roughly in your mind, there is an image already, right? Just roughly capture the scene described by this sentence. So as human being, we have this kind of capability to imagine what does this texture distribution look like roughly, not at the pixel level, but the basic layout, rough structure. And actually in the film production, there are also something very similar to this kind of like rough representation in our mind, which is exactly the so-called storyboard. So this is actually this kind of like storyboard used in the Inception movie by Christopher Nolan. And you can see these several different keyframes, and they have these rough sketches. And there's some notes, and in the sketch, you can see these different characters, objects, what do they look like roughly. And then based on such storyboard, they will actually start with the actual movie capture recording. So perhaps for video generation, especially for generating complicated video, this could be also another kind of like approach that we first from the high-level abstract texture description to generate this kind of like storyboard, and then based on this storyboard, we can generate the exact pixel level, like real videos. So how to generate such a storyboard? As human beings, when I told you about this sentence, you already have this kind of image appear in your mind automatically. This is because over the years, we have acquired such visual prior knowledge about object location, object shape, their relations. But how can AI models represent or learn such visual prior? And more specifically, can nowadays large language models, they are quite popular and very powerful in certain sense of understand the common sense of the world. So can ALM model actually learn and model such visual prior information? So more specifically, this we actually started this problem in our newest paper this year, which is so-called Visual GPT. And this visual prior information actually, more specifically, they could concern about like object location, which are typically represented by the bounding box in the image, or the object shape. They could be represented by either the semantic mask of the objects, or maybe for humans, they have this like skeleton or key points. And for these different bounding box or mask or key points, they have specific layout in the image, and it kind of like defines the relations between different objects and their interactions. So these are actually the rough structure that we would come up with in our mind. So the question is that, okay, we can perhaps learn about this prior information, how they distribute in the real world. But the issue is that all this stuff, they are sort of like in the image domain in our 2D, like in this like 2D image representation. So how can we actually turn it into something can be read or fit into the ALM, which are basically tokens, discrete tokens. So for object bounding box, I suppose that's something easier, right? So you can, just for each object, you have 4 coordinates to represent it, like x min, y max. Sorry, it should be x max and y max. And so for another bounding box, we can also have this kind of like 4 coordinates. So in this way, we can convert this kind of like 2D visual information into discrete sequential tokens, and we can then fit that into ALM for modeling. So similarly for other like human key points and semantic mask, we also have similar ways to deal with that, to convert into basically discrete into tokens. Once we're done with this kind of like conversion, we can actually, design some kind of like this kind of prompt that can be, used to fit into the ALM and so on and so forth to generate the content to imagine about the rest of the image. So more specifically, in the prompt, we define this kind of like different categories, like for example, annotation type, whether you wanted to let the ALM to imagine about bounding box location or key points or mask. And for the data type, there could be multiple instance scenario, or maybe you have an object in the center. And for the size, what are the size of the object typically in this image? How many instances do you have? What is the number of key points used for human skeleton? And also, of course, the category. What is the category for each object? So here is a more concrete example. For example, we can have prompt like box. So we are supposed to generate bounding box, multiple instance, small, 14, person, K, person, and so on and so forth. So this is like the prompt that we fit into the ALM, and what we want as the output is basically the rest. We wanted to let the ALM to imagine what are the locations and the coordinates for all these 14 objects. So for ALM, it's operate over, given this input to predict the rest of the contents, rest tokens is done in this kind of language modeling manner, but they are corresponding actually to something visual. So this is for the bounding box manner. For key points, also we have defined, for example, 18 key points for each person. Then for 1 person category, for 1 person instance, then you would have kind of like this 18 numbers. And this will be the key point for the second instance, second person. And also for the mask, we also have some way, actually it's borrowed from the CVPR 2020 paper to represent it into some discrete manner for representing a semantic mask into this sequential discrete tokens. So in this way, we can actually kind of like discrete the 2D visual world into some sequence corpus, and then just train the ALM on this sequence corpus using nested word prediction, basically standard language modeling objective. Once it's trained, then it's supposed to be able to understand or capture the visual prime information. And here is a demonstration of the learned model. So once the ALM has been trained on, such a visual world data set, then, for example, during the inference, if we provide this kind of like prompt, box, multiple instance, large, 6, cap, dining table, donut, and then we let the ALM to complete the rest of the sentence. And then it can complete, like after cup, dining table, donut, it can complete, or predict the next object might be for cap, and what are the bounding box location coordinated for each of the object. So then this would actually how it looks like. And based on that, based on this layout generated, further on, we can use some off-the-shelf pre-trained layout to image generation models to also diffusion models to generate the image actually. And also more interesting, we can do that in kind of like a diagonal manner. So basically after the first input prompt, if we wanted to further add on something new, we can use this kind of format, kind of like an instruction to further fine tune, to improve and let the model to further complete and generate this like new 2-person. And this is the corresponding layout in the 2D manner. So this is actually work that only for image, but hopefully demonstrate this idea that we can use LLM to generate this kind of like layout. So how to, of course, we wanted to extend it further for especially video generation. And there is this very interesting work called Video Director GPT. It's exactly, it's very similar in the first step using this LLM. Actually, they use, for example, GPT-4 as the so-called planner to come up with this storyboard. Basically, because it's a video generation, so it's not just the one, this kind of one single layout. Instead, they have a sequence of layouts image, right? And actually, more specifically, they design different actually scene, the scene 1, scene 2, scene 3, and within each scene, there is a scene description, text, and also a sequence of frames in that scene. And in each frame, you will define or basically let the LM to imagine what are the objects and their coordinate locations. So this is exactly look like this storyboard. And given this, we can use some layout to video generation model, essentially to generate the real video. Of course, there's something you need to be dealing with, like in this layout video generation. For example, for the same object, you want it to be consistent over different frames and the scenes. So this is one video example generated by this model. Use the storyboard as a condition to generate video. And you can see this description for the scene 1 and scene 2 and so on and so forth. So this was great. So one thing to note is that for this video generation work, unlike in the Visual GPT, which we actually train on larger corpus, here they use the in-context learning method to provide a few, several basically examples as the instruction. So the idea is that because the number of examples we can provide it might be still limited. So ideally, we wanted to let the, even for the video generation, we want the model would be able to acquire some of this kind of visual prior information from a larger corpus, and then that requires us not only use the existing LLM, but need to further fine-tune it on the visual world data. So for the video generation specifically, we wanted to model the so-called long-form video prior information, like in a video as it progresses, how this object position changes over time and the relative size, what is the actions and human object interactions, so on and so forth. So we look out and found there is no existing dataset that would be suitable. So we developed a new dataset, which is called Storyboard 20K. So more specifically for, we have two kinds of annotations. The first kind is more about the character-centric annotations that we annotate the bounding box of the person and their skeleton key points. And because in the movies, it's complete video, sometimes the expression are also very important. So we also have the face key point, and also the hand object interaction is important. So we have the hand handpokes as well. And another kind of annotation is the field set-centric annotations. Is basically more about what are the objects in the background or the useful surrounding objects like the buildings, railway, train in this case. So we have these two kinds of annotations. So based on such, larger data corpus, we would be able to fine-tune train the GPT to learn some more generic video, especially long-form video prior information. And based on that, it will be able to generate the layouts, generate this kind of storyboards that makes more sense and more well aligned with the videos we have seen in the real world. And so for this work, actually, we are still doing some cleaning, etc., and improvement. So we hope it can be released in early 2024. But anyway, in this domain and storyboard, there are a lot of quite exciting works as well. So far, we are mostly actually in this part is talking about these intermediate annotations. Sometimes if we want, maybe the video to be generated is not so complicated, it's just long. There are also a lot of work working on this direction of long video generation, how to generate long video. And the one we'd like to talk about is this new XL model from Microsoft, I think. So the idea for this paper is that it's a so-called diffusion over diffusion architecture. But the idea is that it's a cost-to-find hierarchical generation. Some highlights is trained on very long videos, like more than 3K frames. And it allows you to do parallel inference, so the speed could be fast. And furthermore, they build a new data set, actually of very high resolution, 1000 by 1000 something, and it contains 166 episodes. So let's talk more about this diffusion over diffusion ideas. So first of all, they also need to have, because we were talking about long video generations and what are the contents or conditions for generating these kind of long videos. So in this case, they have basically this kind of so-called nodes, or essentially is a paragraph, a sequence of sentence. So for each sentence, it may be described as, a short duration, a short scene, a short, short, and then you have the next sentence, so on and so forth. So they have, first of all, this global diffusion model that essentially map or essentially given a text description, it can generate a keyframe, something like that. And then they have this local diffusion model, which is used to fill in the gap, basically, what are the missing transition frames between these two, this keyframe and this keyframe. So fill in the gap and to generate more frames, essentially, induce this kind of interpolation, essentially. And more specifically, they actually this is kind of they actually have different layers. So that's why it's called hierarchical generation. For global diffusion, it's just one layer. So basically, if we have L text prompts, then we generate L keyframes. And but for the local diffusion, how to fill in the gap to the interpolation is to fit in these use this as the first frame, and maybe use this frame as the second frame, as the last frame, and then we use the local diffusion model to generate something in the between. And once it's generated, it uses as the last frame, and use this first frame as the first frame, and interpolate the frame in the between. So on and so forth. It will be able to gradually increase the number of frames per second. And in terms of the model design, actually they try to let the global diffusion, local diffusion model to share the same model. But the difference is that their input conditions are different. So for the global diffusion, they essentially here they mask all, mask everything. But for local diffusion model, because it's doing the interpolation, so they need to actually provide the the first frame and the last frame, and only mask the frames in the between. And here are some examples generated by this model, and this like from the very first beginning, and this is a 5 minutes on and 10 minutes onwards. So you can see it can be used to generate this kind of like long video. And there are also other very interesting work along this line for doing long video generation. So the last pieces I want to talk about is the so-called multimodal-guided generation. So basically, what is multimodal? So essentially, you have the idea is that you have multiple multiple signals as the condition for guiding the video generation process. Because this condition we have seen so far is mostly about text. It's mostly about text, or sometimes maybe you have the image, make an image, move. So that's image to video generation still plus the text as condition. But anyway, they are pretty kind of like limited in terms of the number of conditions. So in this topic, we're going to see actually a lot of work, a lot of code in this multimodal guided generation that they explore different kinds of conditions. So the first one is this so-called MC-diff, which actually use the motion to guide the video generation. So the idea is that we provide a starting frame, and then maybe we can let people to draw some this kind of like arrows to indicate how it should move maybe in the next frame. So it's very sparse. It's basically kind of like just indicating the direction of a specific point. And if the condition is different, then the video to be generated are of course different. So how to do that? They have essentially a two-stage generation process. So the first stage is that given the input these directions, so then they first complete the flow. Essentially, they are trying to compute this optical flow, but since the input strokes are pretty sparse, so they first to complete this kind of flow image, and then for the diffusion model, it actually takes the this the flow as condition when together with of course the starting frame for next frame generation. And here are more examples about the video generated, and you can see it well aligns with these strokes drawn by user. All right, so another kind of like modality people could use is actually song. So basically, it's still for this specific work from ICCV, it used a texture prompt together with an audio segment as condition for video generation. So the text prompt is here like a photo of beautiful beach with blue sky. So if based on such prompt, we may generate something else, very similar, but may not be precise in the sense of that at first they are beach, and then you can see some kind of, these fireplaces. So why is that? It's because they have another condition, the audio segment. So the very initially it's just the waves, and then it has the sound of fireplaces. And there are also other works along this line of using the audio or sound as condition. So another category is the image-guided video generation. And actually, we have already talked about this in the previous subtopics when we talk about how to make an image to move, essentially. So that's similar. So basically, the condition, one of the condition is a provided image. And another very interesting work is this actually use the brain MRI signal as the condition. So the task is that they let in this work they let people to watch a video, and then we are trying to record their reaction in the brain, this like MRI signal, and then use this signal as the condition to generate the video, to reconstruct the video seen by the person. And here are some actually their results, like the ground truth, the video seen by the user, and this is the video generated. So you can see they are actually appearance are different, but the actions are pretty consistent and similar. So yeah, that's actually there are a lot of work in this field about multimodal guided video generation. If you're interested, feel free to check them out. For example, the movie factory, the Cordy paper in Europe's diffusion, next GPT, which can, even, like not only condition on any modality, but also generate any modality. Essentially, that's the idea. All right, so that's our first part of the video generation. So I hope you enjoy it. And actually, we, as Chris mentioned, we pull out a very specific topic in video generation into the second topic of video editing. So why is that? It's because there are a lot of products they are actually focused on this kind of application. Maybe people indeed have a lot of demands in editing their own video. So there are a lot of work in this field, in this topic as well, so that we have a very dedicated, separate topic around that. And more specifically, we are going to, divide into actually 5 subtopics. And the first subtopic I'd like to introduce is about this turning-based approach. And more specifically, the turning here, the idea is the turning here means that we turn the video generation model on the input video. And the input video here is essentially the video provided by the user. So since it's just one video, so often we have this so-called one-shot turning scenario. So you only turn on this single video. And maybe based on some textual description, provided by user, they describe how they wanted to change or edit the video. These texts are also conditioned. So there are quite some work in this, like one-shot turnings field. And the one we'd like to introduce is our paper on ICCV this year. And again, the task is that, for example, you have a video of a man is dribbling a basketball. Then when we modify the texture prompt, like change it to James Bond or maybe a prince with a crown, it can accordingly modify the content in the video. And this requires us to actually change the video diffusion model somehow. But the nice thing is that we only need to check on this one single video. So actually, when we start with this project, originally we wanted to do some maybe more broader video generation tasks, but just like the base model, foundation model that we have seen in the first topic, but of course that cost a lot of computer resources. So we think about, okay, can we do something more efficient and less demanding? And turns out this approach we developed actually only requires training on one GPU, and if it's, for example, A100, maybe the training finish within 5 to 10 minutes, because it's, after all, it's just training on one single video. So the idea or the motivation of this work is that, for example, for the spatial diffusion, this kind of image model, text-to-image model, they can already capture very well about the appearance of the, corresponding to the texture description, Spider-Man and on the beach, cartoon style. So the only thing is that they are not consistent over time. But why not we just sort of like borrow this kind of appearance from the image model? And for video generation, since the task is mostly about the difference or unique thing is about the dynamics, the motion. So in order to better learn the dynamics, can we just provide a reference video to let the diffusion model, the video diffusion model, to learn the dynamics from the user provided video? So for example, a man is spinning, and then we borrow the appearance from the T2I model and change it to the our Spider-Man is skiing on the beach. So to do this task, we actually did some exploration first and found, have arrived with some observations. So the first observation is that for still image, just use the image generation model, and they can already accurately present the warp turns to some extent. For example, a man is running on the beach. When we look at each image individually, you can see, and actually this is running. So if we just run this kind of T2I model 4 times, then you get 4 running images. So they are good in the sense of running, representing the running, and also representing a man or the beach. Appearance are perfect, but the only thing is that they are not consistent over time. So the challenging thing or unique thing of the video is that how to make them, this is V1, V2, V3, V4 to be consistent over time and have smooth motion. So one simple strategy that we learn when we do the foundation model based model is that okay, we can add in some temporal layers, right? So if we just extend the spatial 2D attention into spatial temporal 3D attention, that's great. It can already generate this kind of like consistent video over time. So this is perfect. But the issue is that the memory will explode because the computation, it actually needs to do this like spatial temporal attention across 3 dimensions. That's pretty huge in terms of the computation. So we come up with something, this kind of like very straightforward, but much more efficient attention mechanism, which is we refer it as the so-called sparse causal. But the idea is that for every frame, we only attend to the first frame and also its previous frame. So for example, this is the 3rd frame. Then we do attention only between this frame and also the first frame and the frame just before it, which is the 2nd frame. And for the 4th frame, then we do attention with the first frame and also its previous frame, which is the 3rd frame. So that's the idea. So it saves the computation law, and we found out the performance are actually comparably good. And more specifically, some technical design, like for the 2D convolution, we essentially change it to a pseudo 3D convolution with the temporal dimension kernel size to be 1. And also we add in some temporal attention layers. And also for spatial civil attention, we actually change it to be spatial temporal attention. And actually, during training, we found that it would be good. Actually, we just change this spatial temporal attention layer and the temporal attention layer. That give us the best performance. Another strategy we found to be quite effective is the DDIM inversion. So yeah, as we mentioned in the fundamentals, the DDIM inversion is essentially use the chained denoiser to derive what is the initial noise that can actually lead to or generate this image. So it actually preserves some structural patterns of the input image. So given the video user wanted to edit, we first run the DDIM inversion to get the noise. And this noise, although it's noise, but it sort of still captures some patterns about the input image and video. And once we use that as our condition for denoising, because the noise, they are consistent over time, so it actually ensures the consistency for the video generated by our model. Here are some example results generated by our model. For example, a man is skiing. We can, for example, change it to wearing pink clothes at sunset. And like this dribbling basketball example, we can change to James Bond or Lego man in a black suit. I think what's more exciting is this example. A rabbit is eating a watermelon on the table. And, we can remove this, like eating a watermelon, so you essentially remove the watermelon, or you change it to cheeseburger, it can change to cheeseburger. So it's actually pretty significant object change. This is quite interesting in the sense of, like, in the period scan era, we can still do this kind of, like, it's actually GAN is very good at this kind of, like, style transfer, this works. But it's a little bit challenging for GAN to do this kind of very significant object change and changing into, especially kind of like in an open domain, whatever is this kind of like objects. And also this kind of technology, turn on video, can be also used for test, basically any this kind of like text to image models. Even maybe people have customized it to be their own domain data, for example, modern Disney style, and then we can still use this kind of technologies. And these are other domains like the anything V4.0 and Mr. Potato Head. We can also use this different text to image model. And here is a quick application showing that what if we don't use this spatial attention? What if you don't do the inversion? And what if you don't fine-tune the model? And yeah, so you can see that all these three technologies are important. And in terms of the evaluation, we look into two dimensions. One is the frame consistency. Essentially, is to, like in the clip score case, is to compute the clip embedding of every frame, and then you measure the similarity in general, in average. And or you can just maybe ask the user to, rate and compare given two videos from different models respectively, which one is better. And for textual alignment, that is how well it can, describe or correspond to the sentence. Another this kind of like one-shot turning strategy or method is the so-called GMX from Google. So the main idea of this paper is that they do mix the video image fine-tuning. So given this, given this input video, we would also kind of like shuffle it into an ordered set of frames. So during training, they have used the same model, but they have different mechanisms to dealing with these two different input data modality. So when the input is the video, then we actually need to change this temporal attention layer, convolutional layer. But if the input are just an ordered set of frames, then you process each frame individually. So they basically frozen this temporal attention layer and do this so-called masked temporal attention. But anyway, the idea is more about you process each frame independently. So one thing to note is that they actually built up this framework on the image and video model, which was the the base model, video generation based model from Google. It's a pretty strong video foundation model. And then they fine-tune it to generate individual frames or maybe the video as a whole. So once the model has been trained, then it can be used to do, like the used to do this kind of video editing. So in the video editing or inference stage is the things that we provide the given the user provide the video, we first downsample it and add on some noises. So it's kind of like trying to preserve, still similar to the DIM inversion idea, is preserve the information in the input video, but then use the new text and fit into the fine-tuned GMX model, and then so then you can generate the video as described by this text. And there are also other one-shot turning based approaches, like this video P2P and also this modified self-attention for better temporal consistency. So one thing to note is that for this one-shot turning methods, they are always, actually every method, they always have pros and cons, right? So for this one-shot turning strategy, because here it still requires one video or one shot for training. Later on, actually, we'll talk about methods that do not require any training at all. So that's pretty efficient. But for this kind of like approach, they still requires one video for training. So the advantage it will bring us is it can support significant shape change. So like remove a watermelon or change it to something very different in terms of the appearance and especially the shape. This kind of one-shot turning strategy is more powerful. But for the training-free approach, they cannot handle this kind of large significant object shape change. So training-free is another extreme, right, compared to one-shot training. And another extreme on the opposite direction is essentially we train on more videos. We train on more videos. Like for example, eating a watermelon, can we have many, not many, but multiple eating watermelon videos? So that comes to the next scenario we like to introduce is about multiple shot turn. It's still fall under this like turning-based approaches, but we like to use basically more videos for turning. It's kind of like give you a better idea of a specific action like skiing. What does it look like? Maybe one video is not enough and you would like to provide more reference. And the paper we like to introduce is so-called motion director. So let's imagine what does a monkey playing golf look like, right? So we know the motion of playing golf, and also we know the like appearance of the monkey. So as human being, we would be able to synthesize and then come up with in our mind what does this look like. But it's challenging for the video generation model because they don't know about this specific motion. For example, we actually test out the foundation test to video diffusion model, and they can synthesize something like a monkey holding this grape, but it has no basically this kind of motion. So in order to power the model to synthesize this kind of video, this kind of like playing golf video, we provide with our model a set of reference videos. Instead of just one video, we provide several videos that are all about a person playing golf. So it learns more, precisely about this like motion. And the good thing about this like model or this module we propose to learn is actually something that can be sort of like look like plug into the base model, foundation model, and when we do the training, we only change the motion director, but with the diffusion model base model frozen. And so let's first take a look at the result it can generate. So with this kind of technology, we can, of course, customize a specific motion. For example, lifting weight. You provide several reference video for that, and we can synthesize various lifting weights. And most interesting, we can even learn the motion about the subjects and also the camera. Like here, this is like in this video, actually we provide a surround shot of a villa in a garden, and then actually you can learn this kind of specific camera motion and generate different multiple views, like for example, a pyramid in a forest. And also for this car, when it drives along this direction, and also this kind of like motion of driving along this direction can be synthesized into other scenarios. So how we make this happen is that we are developing a model that decouples the appearance and motion. So why we want to do that is because we have several reference videos. And the thing we wanted to learn is just the actual motion. We don't want to learn much about the dependency, especially dependency of the appearance. And the difference in different videos, they are different. So it's not something that we wanted to fit into our model when we just trying to learn about the motion. And in order to do that, this is not that I guess like straightforward. because sometimes these two things are always coupled and cannot really avoid of overfitting on this like appearance. So that's why we come up with this two-stream network. So the first stream or first pass is actually training the so-called spatial LoRa, and the next temporal stream is training a temporal LoRa. So in the first spatial pass, we actually fit one frame at a time in order to compute the spatial loss. But the idea is that this pass is used to use this green module, this LoRa, to learn about the appearance. But when we later worry about concerns about the motion learning, then we have this like blue blocks here, blue modules here that are dedicated to learning the temporal dynamics, learning the motion, and all frames are fit at once. And more specifically, later on, we actually devise this appearance, the bias temporal loss. But the idea is that we even further do some kind of like normalization to eliminate the effect of the appearance over the temporal loss. And with this kind of like technology, we found that we can do something even more interesting in the sense of we can mix like different videos, concepts in different videos. So this is, for example, the first video, and this is second video. You can see this video, this car drive along this direction, and this is another opposite direction. Because we achieve this kind of like decoupling effects, so that we can actually use the motion of the first video to mix with the appearance of the second video. So this is the appearance from the second video, but it's drawing along this direction, same as the first video. So similarly, we can mix the motion of the second video with the appearance of the first video. And we compare our method with some baselines. For turn video, of course, we can also extend turn video from one single video to multiple video. But the performance is not that good in the sense of it does not learn about this motion. For the base model itself, originally would not be able to generate this kind of motion. But if we couple this spatial, temporal, this appearance motion thing learn together, it can learn the motion, but you see it actually overfit the appearance of the input image. So it overfits too much, includes something, this kind of appearance that we don't want it to include in the motion. And you can see in our result is that once we do this decoupling, the result is much better. The appearance would not leak into the video we wanted to generate. And even with this normalized loss, it is even better the results. In terms of the quantitative evaluation, also we use the automatic metrics as well as the human evaluations, and mainly look into 3 dimensions. One is the appearance, like if the model is overfitting the appearance of the reference video, then the diversity may not be that good. And the temporal consistency, how is the consistency over time, and also the motion fidelity, how will actually the video generated correspond to the motion that we want the model to learn to customize. And here are more examples, like provide reference videos of skateboarding, and you can generate this kind of beer skateboarding, and also this like celestial camera motion. All right, so far we have talked about video editing methods that requires training on either one single video or multiple videos. So there are actually also quite some working on training-free approaches. So the first one I'd like to introduce is this one, so-called token flow. So as always, the main challenge to do video editing or video generation is there to maintain temporal consistency. So in the specific video editing case, if we edit the video using image technologies that edit every frame independently, so you would have some kind of like inconsistency over time. And this paper is basically dedicated to resolve this problem. And the main idea they introduced is to enforce the so-called inter-frame correspondence. Basically, from the original input video to be edited, they found out the correspondence across frame, and then they try to enforce such correspondence in the video generated or in the final edited video. And the main idea technically is that, for example, for this dog, for example, the left eye, we can find this correspondence, basically the same semantic point, same semantic part in other frames. And then in the unit, we extract these features or tokens. so then for a specific actually page or token, then you would be able to find out its corresponding locations in other features. And we record actually this correspondence. And this is in the for the input video, the video to be edited. So during the actual generation of the new video, basically the video edited, basically it's a denoising process. And then what we do is that for the current frame, we actually do not directly use its feature. Instead, we use feature from corresponding positions in the preceding and following frames. So you use the previous frame and the next frame, their features for the same part. So in this way, they can ensure the temporal consistency. And as you can see, it's at least much stable than the per frame editing results. And there are also other approaches like this one, so-called phase zero. And the idea they proposed is to manipulate over the cross or self-attention maps. So the basic idea, of course, is that during the denoising process, during the generation, you would use the DDIM inverted noise to provide a pretty good initialization. So this is the very basic techniques, but what they proposed is further, they actually, during the inversion process, they save the self-attention and cross-attention maps and fit these maps in the denoising process. So what they do, or why they would like to do that, is because, for example, if the input video, the video to be edited, is maybe a JIP in the counter side. So in the cross attention, actually we would be able to find out, hey, for this token JIP, what is semantic map like this? So then you can get a rough, this kind of like segmentation maps and use that as this so-called mask. So the idea is that because in the input video, in the original input video, we maybe only wanted to modify the main subject, for example, change the Jeep to Porsche. So for the background content, actually we wanted to retain, we want to keep the background. So we wanted to basically keep the features also for the background in the original video. So with this mask, we actually mask out the Jeep part, but keep the background part. And this would be our first part put here. And then the second part is actually about the center location, basically the center object to be edited. Because here we wanted to modify Jeep to other maybe Porsche. So during this is actually the in the denoising process, which is actually generation, they will generate, for example, the feature maps for Porsche. But we only wanted to keep the part of the foreground, but the background part, we perhaps do not want to use this kind of generated new contents. So we actually use this inverse mask, basically only keep the foreground part as this part, and then finally blend these two together in the attention layers, in the attention maps. And here are their results. Phase zero, as comparing to like to a video which requests one video to change. Then you can see the performance, for example, change car to Porsche car or and water painting style is quite consistent, comparable to the performance of the turn-on video, and the video frames generated are quite consistent. And there are actually more work of this like chaining-free approaches. So the next topic I could talk about is control editing. So so far we have been talking about how to use maybe texture prompt to control the video to be generated. But in many cases, user would like to provide phonogram directions or guidance about how the video should be edited. So in that case, maybe they want to provide some depth map or human pose. And even more, even user does not have such kind of demand. When we think about how we can better maintain the consistency between the input video and the video edited, sometimes we can also use such phonogram control like the depth map or canny edge. Basically, extract this depth map from the input video, and we want to make sure in the video edited, in the video, new video generated, we want this depth map extracted from the new video still are very consistent with the input video. So in this way, we sort of like adding more explicit constraint of the video generated. And there are actually quite a lot of work along this line, and we roughly divide it into 3 categories. One is depth, another is pose and point, and also other conditions and their combinations of multiple different conditions, which can be summarized actually as a video version of control net. So let's talk about depth control first. So Gen 1 from Runway, this video-to-video translation app is using depth control. So there you can see the input video, basically do some kind of like style transfer, and you can see the input video and the edited generated video are very consistent with the input video. How they ensure that is using the depth condition. So by the way, for depth, they use off-the-shelf tool, which is so-called MIDS, to extract the per frame depth map. So given an image, you can extract its depth map. You can see it's pretty good. And then for the video generation pipeline, they base their model on this 2D stable diffusion. So we need to do some 3D inflation first. And then we also insert some temporal convolution layers, temporal attention layers. And finally, we can start to change this basically video editing model. And the key difference is that besides the latence or the noise, they input into the UNet. Along with that, they have this yellow bar here, which are corresponding to the depth maps actually. So these they use the MIDS to estimate per frame depth and use some encoding to encode into latence as well. So the latent of this depth map concatenate together with DT in basically used together as another kind of like condition for UNet denoising process. Once the training is done, the model can be used to do video editing for any input video. So given a video, the process will be look like you extract the depth condition of the input video and feed that along with DT, and then the output, this decoded video will actually maintain the consistency, especially the depth map condition in the generated video. So one thing to know that the kind of like the control net, you need to train or enable the model have such capability of conditional on the depth map. You need to train on your set of videos. But there are also approaches that does not actually require any training or fine-tuning at all. And you can see in this paper, when they do per frame editing without any technologies, the head of the pig would basically be, the editing result would be different, would be inconsistent. But using their technologies, the general results are pretty consistent. So how do they ensure such temporal consistency even without any training and fine tuning. So perhaps you already guessed it out. The first thing we will to do is DDIM inversion, and use that DDIM inverse the noise as the initialization for video generation or denoising process. So for the first frame, we run inversion to obtain the initial noise, and second frame also we have the initial noise, and use that correspondingly for denoising. And to further ensure the temporal consistency, over time, they need to relate, the first frame's denoising process and the second frame's denoising process. So what they did is to inject the self-attention features from the previous frame unit for generating the current frame. So these are talking about these arrows here. So the features from the first unit, first frame, from the previous frame fit into the current frame, the next frame. So you sort of like smooth out, basically provide some smoothing between the previous frame and the current frame. And then similarly, when we talk about the final latent, they also, when we try to update the current latents, they also use the latents of the previous frame to provide some kind of a guidance in updating the current frame's latents. So you make the features and the latents more consistent and smooth across time. And there are some of their results you can see for this like car moving, and also person surfing, skiing, and you can see it's I mean, afterwards it does not need training or fine tuning, so I would say it's pretty impressive. And then further on, people trying to leverage and inject more conditions, right? So like Canny age map, and they can use also combination of all these different conditions. So let's talk about there are actually quite a lot of this video control network. For example, this one, training-free controllable text-to-video generation. And the idea is simple to just input the structured conditions through the control net module. And they use the like depth map or age maps. So, we first, again, borrow the stable diffusion and control net from the 2D image. And then they are, we don't need to actually change them at all. And then we inflate them along the temporal dimension so that they can generate video. And that's it. And maybe one more thing they further improve the performance is the so-called interleaved frame smoothing during denoising, so that can achieve even better temporal consistency. So what they did is that it's again actually some kind of smoothing across different frames. So the orange color here means the frames have not been smooth, and green frames smoothed. And you can see for I-2, it has been smoothed from the previous frame and the next frame. But for I-1 in this step, it's not smooth, but I-1 will be smooth in the next 10 step. So anyway, in this correct iterative process, all frames will be smoothed. And here are some of their results. Like this is the input original video and the depth condition, and this one would be the ages condition. Comparing to the turn video and test to video 0, I think this example is even more significant. Like the dog is pretty consistent with the dog in the input video. This would, definitely thanks to the age map provide very good guidance of how the video should look like. And there are more examples of results on depth map control and canny age control. And of course, for human, you can use the human pose as a control as well. There are actually a lot of work doing, this like video control net. So for example, this one adding additional conditional control for one-shot text video editing. And also this one, video control net. So one thing to know is that for this one, they trying to also use the optical flow for to guide the video editing, and they borrow the concept from video compression like IPB frames. So iframe is actually the keyframe. So in video compression, like they have this concept of GOP, group of pictures. So typically they have like keyframe, iframes that you have the RGB values, and for P frame and B frame, we don't store actually RGB values for every of these like PB frames, but instead we store some of the so-called motion vector, and basically the motion vectors kind of like warp or tells you how you can actually manipulate to move the pixel from the iframe, the keyframe, to the next frame, for example, the P frame. And there are also this work re-render video, which actually also leverage control net, and actually further they combine several and come up with several strategies to ensure the consistency between the input video and the video editing. So maybe one thing to know is that the result is pretty awesome, especially in the sense of you want to do some style transfer, but this kind of consistency between input video and output video in this case of style transfer is great. But in some cases, if you wanted to edit the video to, for example, change the shape of a specific object significantly, then this consistency maybe actually becomes a drawback in that case. So in that case, maybe you can use some turning-based approaches without such very strong constraint. There are also other works along this line of control net, and they provide additional, basically different kind of like controls and putting them together. For example, the CC edit, they have appearance, basically they have this appearance control net, and also they have the structure control net, like using the condition of depth, soft edge, etc. And this work, Video Composer, is quite powerful in the sense of they explore a large variety of different controls, like provide the single image as a control, or sketch, motion vectors, depth map, mask, sketch. And in terms of the implementation, I think it's straightforward. So essentially, they have this spatial temporal condition encoder. They have been trained for dealing with different kind of modalities, and even also is a unified input interface for conditions, so that you can actually fuse these different conditions all together. And let's see some of its results. This is providing the sketch sequence, and this is let people draw some of the handcrafted motions. All right, so if you're interested to try it out, feel free to do so. And there are actually more work along this line of control net or depth-based video editing. So the next category I'd like to talk about is actually about pose control, because they're very intense interest about actually control the video of a human. And actually for video editing or video generation, human videos are always a very important topic. And the task that people focus on in this scenario is that you have an input image of somebody, and then from the video to be edited, essentially we extract its pose sequence. And then the task is that how we can use this pose sequence to guide this image, this person to, for example, move. So you can see in this case, we have actually two conditions. One is the input image, and another is the pose sequence. So there are a lot of works along this line as well, and there is one recent work from our group, which is called Magic Animate. And this is the reference new video, new image, and this is the motion sequence, pose sequence we extracted from the input video. And you can see that we can make it dance and move according to the motion sequence. So people have been, studying this actually task for quite a long time, and they are definitely very remarkable progress so far. But you can see there are still in many cases that we have this kind of flickering video, or maybe you cannot maintain the consistency of the background. Or sometimes we can do that, but the animation are pretty short. They cannot generate long videos. So we propose some technologies to overcome the challenges in the sense of doing a better job of temporal modeling. So this is our framework, and we test out on actually two different data sets. One is the TikTok, this is a dancing video data set. Another is the TED Talks videos that we have people giving, TED Talks. And for this work, we do actually need to train our unified module. We do need to train a unified module, so that can learn about the motions and how to retain the background, etc. So once it has been trained, it can be used to animate, to process any input single image. So we need to first talk about the training part, and then later on we'll talk about this inference part. So for the training part, this is the center, the conventional UNet. This conventional UNet. So we have basically two kind of like injection here. One is, of course, the control net for pose. So we have a control net for pose so that you can make the video generated according to the pose sequence. And then another challenge, because it's to how to maintain the appearance of the reference image, like the background and the appearance of the person, how to make sure it's maintained. And what we did is that we have a trainable copy of the UNet. You have a trainable copy of the UNet that are specifically dedicated to process or adding on this condition of reference image. So through this copy, we can insert different layers features into the denoising the UNet for the final video generation. So we need to actually train these two modules on, it's not that large, a few hundreds videos, but still we need to train it on our generic data set. So it learns about the basically accrues the capability of control pose and also maintains the appearance of the reference image. So once this has been trained, then we can follow this inference pipeline. And during the inference pipeline, you only need to provide the pose sequence and also the reference image. That's it. You do not need to do any further fine tuning or whatever. You can just use it. But there are several strategies we have used to make it produce better results. So for example, for the input pose sequence, you can see that actually instead of having one sequence, here we actually have multiple sequences. The reason we have that is because we wanted to have some overlap between the sequence. So given the first sequence, second sequence, we actually let them have some overlap. This allows us to generate smooth results. And also further on, we'll talk about this, also help us with generating very long videos. And another thing is that because now we have multiple sequence, and for all these sequence, we actually use the same noise. So again, noise, it provides some kind of, like initialization or information about the structure. So ideally, if we wanted to maintain consistency over time, then we use the same noise as initialization. And then given the reference image, we can combine all this together to fit into the trained model for denoising. And for the sequence 0, we have a denoised sequence. And for the sequence 1, we have another sequence denoised. Because they have overlap, so for the overlap part, we can average them to, this is kind of like a smoothing operation. So with this technology, we can generate actually long video, and they have pretty good consistency. And here you can see our results comparing to some of previous methods in making this reference image dance. And also this is the comparison on the TED Talks data set. And more interesting, we found that this animate module can be actually used not only for the specific training data domain, but also can be used to animate unseen domain image. And there are also other works along this line, basically using the pose as a guidance as a control. So the next topic we'd like to talk about is about control using points. And this was brought up in our recent manuscript video swap. So the idea is that, given the source video, we wanted to swap or change the subject from the specific object to another concept, another target subject defined by user, maybe using a few images of this specific concept, this specific dog. And then in the edited video or the swapped video, then we can see the motion of the objects actually pretty well preserved in the generated new video, and also the background should be preserved as well. And many methods we have introduced so far, they are actually can be used for this purpose, and they are promising, can produce some promising results. But maybe one challenging or issue is that in many cases, if you look at the fine-grained level, then the movement of specific parts may not be well aligned between the source video and the target video. And then how we can actually make a precise, correspondence between the input video and the source and the generated video is that we consider, as human beings, we pay more attention to these semantic points like left eye, right eye, both ears. So if we can keep the trajectory, keep the movements between the source video and the target swapped video, then this would ensure this kind of very good correspondence and aligned motion. And to do that, that's main focus of this work. And we start with some toy experiments and obtain some empirical observation and findings. Basically, the first question we'd like to answer is that whether we can use these points as sort of a control for a specific, source video subject. And we're learning that on only a small number of source video frames. So basically, given the source video, we manually define and annotate a set of semantic points like this, annotate them on every frame. Actually, in total, we have 8 frames. So there's a small number of source video frames, 8 frames. And we wanted to essentially just to see whether these points, these point maps, they can be used as a condition for, condition how the new video to be generated. And because we are using this as control, so we definitely need to introduce a control net, and specifically we use the T2I adapter in this case. And the input of the condition for T2I adapter is the point map. And then once we actually train this, T2I adapter on a small number of source video frames based on such new points condition, we found that it can be generalized to deal with new points. So basically, if you reject the points, for example, if you reject point from here to here, then you have a new condition, you have a new point map. And the chain D2I adapter can actually generate new content based on such new points. So this tells us it is actually possible to use these semantic points as the condition for control how the videos to be generated. And also because we can extract the trajectories of these points in the source video, and if we enforce that for the video generation for the denoising process to generate the edited video, then we can maintain these motion trajectories in the source video. And another interesting observation we have found is that for this set of jagged points, if we jag only part of them, actually we would be able to modify the shape of the object. So based on these findings, we come up with a pipeline to do point control. So the system actually is, the diagram is complicated, but system actually only has 3 parts, not that horrible. So the first part is basically just the DDIM inversion. Given the source video, you do DDIM inversion to obtain the inverted latence. So the inverted latence, as always, it will be used as the initialization for the DDIM denoising process. So it can help you preserve the structure of the video and also help with the background. And of course, for the DDIM denoising, we do this kind of like latent blend technologies so that you will be able to use some of the features and latents from the source video so that help you with the background preservation. So actually this comes up to the second part of the DDIM denoising. That's the generation of the new video. You can see this is the, for example, the new video generated. And the third part, which is the core component we introduced in this paper for adding this kind of additional point control, is the semantic point correspondence injection. And we will talk about how you would be able to design this module for point correspondence injection. And there are some other detailed designs of this model. For example, we use the pre-trained T2I model weights actually in these like gray bars. And for the blue bars, it is basically trying to inflate the video to have the temporal capabilities. So there are motion layers, and more specifically, we use the animate diff, the pre-train, and we use this to fix the weights so that it will be able to ensure temporal consistency. And also we have optional ED, so-called ED LoRa. So this is a technology from our newest paper, so-called mix of Shou. So if you wanted to actually do concept customization, for example, provide a few images for this dog and then learn how to generate this specific dog in the denoising process by just this test token, and then you can use this ED LoRa. But of course, if you don't want to do customization, you just wanted to generate another concept which has already maybe learned embedded in the stable diffusion, then you have basically no need to use ED LoRa, so that's it's optional. And the main design module is semantic point correspondence injection. We have several design aims. So the first one is definitely to use this to guide the motion trajectory to make sure the motion trajectory are consistent between the source video and the tech video. But unlike in the toy experiments where we ask human annotators to indicate the semantic point over all frames, we know this is a very human, labor-intensive process. So we wanted to reduce these human efforts of annotating points. So this comes out with our methodologies of doing point control. And the first step is actually extract this semantic point. And to reduce the efforts in annotating points, we only let user define point at one key frame. Let's say here are so many frames, and we only annotate the one of the frame, key frame, and then the in order to obtain the points, their coordinates on other frames, we use some existing technologies like point tracking or detector, so they can propagate these annotated points to other frames, And then the next step is that how we can get some kind of like representations or embedding for the semantic point, because we want to use that later on as a condition for generation. And more specifically, we use this so-called DIFT. So it's essentially some of the intermediate unit features. And then for each semantic point, we can get one this like embedding vector. So more specifically, you have the coordinate for each point, and on these like DIFT feature maps, and you can, for example, if you have 3 points, then you can get 3 different colors, it's like different embeddings, and you have the embedding for the first frame, second frame, third frame, so on and so forth. And finally, because for one single point, we only need to, although it like moves over time, but for the semantic, embeddings, we only need one vector. So we do some aggregation over time. We do some aggregation over frames. So therefore, finally, for each point, you have one feature vector, embedding vector. Then the next step is what we so-called semantic point registration on the source video. So it basically tells us, or trying to learn, it's basically trying to learn these a couple of MLPs. So a couple of MLPs maps the semantic point embedding we obtained from this step 1. We use that, feed that into the learnable MLPs, and then to produce several projected features. And these features will later on use as the condition for, later on use as a condition for generation, for denoising the unit. And more specifically, we have 4 MLPs here, and they are corresponding to different scales, 44, 32, 16 by 16. And then here is actually, it's for the very specific, for example, eyes frame, but later on, when we try to obtain the condition, we have a condition for every frame, from first frame, third frame to end frame. And for each specific, for example, this group point, the embeddings over time, they are the same, but the coordinates, they change, they move across frames. So that's why it will like also move sort of like in kind of like a trajectory manner. And then we have different scales corresponding to 4 MLPs here, and use that as the condition. So in order to actually train these projections, these MLPs, we need to, of course, define some objectives. And specifically, definitely we use the denoising, the diffusion, reconstruction loss. But here, because we only concerned about the point, so we only reconstruct the local patch around the point. And also a strategy we found to be useful is the so-called semantic enhanced schedule. So we actually only sample higher time step from, for example, half t to t. We found that this is helpful in the sense of that will not allow our model to overfit into the low-level details, because maybe at time 0 is too close to the original pixel, so that like overfit to the low-level details. And after these 2 steps, our model has been optimized to learn how to use the trajectory of the input source video. Basically has already registered these semantic points into your motion, the new video generation process. And then once it's done, we can use the model for various applications. So for example, if you have another concept, for example, this cat, then you can see that we swap the source video star to the target concept, and the motion trajectories very well preserved. So this is an easy case in the sense of that these two concepts, they are very similar. They share actually all the semantic points. But there are also other cases. For example, in this case, the airplane, and we wanted to change it to actually helicopter. So they are, of course, similar, but the shape are still quite different in the sense of that we wanted to, actually, we would be able to remove some of the points. We can only use part of the semantic points, basically only those parts that we wanted to enforce the correspondence, to enforce the, to retain the original motion trajectories. So you can see this is the helicopter videos. And more specifically, interesting, we can do shape morphing. For example, when we try to change this car to this car, of course, we can use the original trajectories, but it does not make sense to some extent because their shape varies a lot. So why not we just move the trajectories of the source video, only source video a bit to fit the new object, to fit the object of kind of like very different shape. So this is a bit actually tricky because when we ask the user to drag the points to like suit the shapes they want, basically we ask the user to modify to do this like to modify the shape of the object. But dragging that at one frame is straightforward, but it's not that straightforward of how to propagate such displacement over time to other frames. So if you are trying to just find out the correspondence, say for example, this point and is in another frame is maybe this point, another frame is this point. This kind of like correspondence is easy to obtain by matching the similarity of appearance. But if we are talking about dragging or morphing the shape of the object, if we wanted to move this point to here, if we want to make this movement, okay, but how this movement or displacement would be achieved in another frame, in this frame, or maybe in this frame, where is the point? It's not that straightforward. This is because the camera also moves and the subject is moving as well. So how we deal with that is we resort to the so-called canonical space. And more specifically, we use a technology called layer neural atlas. We will introduce about this technology later actually in detail, but the main concept is that they can kind of like aggregate all these frames into one 2D image, aggregate all frames into one 2D image. And then that's why actually it's called canonical space. And then when the user define how to inject this semantic point on, for example, this frame, then we would be able to determine the displacement in the canonical space and further on to propagate that into other frames. So you use this canonical space as a proxy to complete the displacement translation into other frames. Okay, so with that, let's see some examples. For example, we wanted to change this black swan swimming in a pond to black swan to this specific dark. Then if we do not really do this, we do not drag, then this would how the dark looks like. So the neck is a bit actually long, same as the black swan. But if we actually drag the trajectory of the original, for example, the semantic point here, this red one, if we drag it to be here, then use this this modified trajectories as condition for generating the new edited video, then this would like the duck's neck would be like more reasonable in the it's much more reasonable actually in this case. And here are more examples that we are trying to actually, for example, in this sliver gyring down our query road in the countryside, that we are trying to change the subject into other, like this kind of like car, this kind of like Porsche, so on and so forth. So we use a few images to define the new concept, to customize the new concept, and they can be used in the video edited. And also, of course, you can use some concepts already learned by the image model which we use as initialization, like airplane change to UFO. And these are examples for swapping animals. And these are the different concepts customized by user. And for others without V, their concepts are already learned. And here, this is the specific example that we also showcased comparing to the previous method, like a turn video, phase zero, render video, so on and so forth. When we trying to change the source video to helicopter, actually all the previous methods they fail, but our method video source would be able to kind of reflect the correct shape of the helicopter. This is because we can, remove some of the semantic points that are not designed in the new concept. So this way, we would be able to support actually shape change in the swap results. And of course, we did some human evaluation of our result comparing to the previous method. Basically, we ask a user to compare whether comparing these two methods, our method versus the previous method, which one is better. And you can see our results the rating for our method is they are much better. Yes, that's for point control, actually control editing. And the next topic we'd like to talk about is 3D aware video editing. And there are a couple of approaches that centered around this 3D aware domain. And actually, for the first one we'd like to introduce is exactly the one we just mentioned, layered neural atlas. So let's talk about this atlas stuff in detail. Basically, the concept is that given input video, we can convert it into two atlas, or actually basically two 2D images. So the first one is foreground, and the next one is the background. And this foreground atlas basically an aggregation of all the foreground across different frames in this whole input video. And the background then are aggregated from other frames' backgrounds. And then we can use that to reconstruct the video. So in this way, we decompose a video into a foreground image and a background image. Then when we think about video editing, what we can do for example, edit this foreground or edit the background. Of course, you can, for example, add some this kind of effects on the background, and it can be propagated back to the video and maintain actually pretty good consistency over time, because we projected this, we conducted editing on the canonical space and project or propagate into different other frames. So they all come from the same source, they are consistent. And of course, instead of manual editing, you can also use some for example, diffusion method to change the background, So for example, in this paper, so-called with edit, zero show and spatially aware test-driven video editing, they edit the background atlas by using some diffusion model, image-based diffusion models. Once the background has been updated, it can be propagated to all other video frames. And there are more works actually along this line. For example, stable video, shape aware test drive, layer video editing. Both books are along this line for atlas-based video editing. And more specifically, let's take the stable video, for example. Again, so it has this background atlas and the foreground atlas. So the background atlas, they use some actually similar to Gen 1, they have the MIDS for depth estimation. So hopefully you can preserve the the input image structure better, and then use this diffusion model, image model for background editing. And then they have and then for the foreground, they actually process this keyframes separately or autoregressively. So for this first keyframe, they extract the foreground and then use diffusion model to edit it to be, for example, this red one. And then actually for the atlas, is not directly extracted from all the foreground images. I mean, it's actually constructed by the so-called partial atlas bank. So from the first keyframes, this like original, still in the original 2D image space, this like original image space, they only mask out this kind of like a foreground and then projected the edited version into the so-called partial atlas. Because it's not aggregation of all frames, it's only contribute, I mean, can only contribute to part of the partial of the atlas. So what's it called partial atlas? But this partial atlas will be used as condition for the generation or editing of the foreground of the another keyframe. So this kind of like impose the consistency of the editing style between the previous frame and the current frame, and so on and so forth. We would be able to kind of like obtain a sequence of partial atlas. And then you can, of course, aggregate all this like partial atlas into the real foreground 2D atlas. So this is how the stable video approaches this problem. And we can see some of its results. It's a trend. This is the original video, and this the texture prompt of the new video should be how it should be edited. It's pretty well. So Atlas is great in this sense of the 3D aware, or more specifically, they have a canonical space for editing and then can be projected to other video frames. But it's essentially not really 3D, and they have some kind of like limitations. So for this Atlas itself, cannot faithfully reconstruct intricate video details. If there are some motions that are subtle, for example, blinking eyes or slight smiles, they are very likely would be missed by this approach. And the estimated atlas typically they are distorted. They are typically distorted, and there could also lead to some loss of the semantic information. So in a recent paper called DEF, content deformation field, they are inspired by the recent dynamic nerve works. So like nerve is for it's a very promising effective technology recently people proposed for multi-view reconstruction. And dynamic nerve, that means that they extend this multi-view 3D reconstruction to even 4D, adding the dimension of the time. So inspired by this work, they come up with a new way of representing video. Basically, decompose the video into a 2D canonical image and a 3D deformation field over time. And then the edited video becomes like editing the canonical 2D image and also then the deformation field. So the more specifically how this is achieved is that they have two nerve-like MLP. So this is two MLP. One MLP is used for deformation field, another MLP is then for the canonical field. So basically, for the first deformation field, we can provide any video frame coordinate XYT as the query, as the input, and given this video frame coordinate, we would be able to map it through this MAP, map into a 2D coordinate. And this 2D coordinate is corresponding the basically the corresponding location on the canonical image. So it's essentially given this coordinate in the video frame XYT, we found out where is this point, where is this pixel in the canonical 2D image. And then now we still don't know what is the RGB value for the specific image coordinate. Then we have another canonical field MLP that takes X prime, Y prime as input to map it into the, to query out basically its actual pixel value RGB. So this canonical field, because it can convert coordinate in 2D image coordinate into RGB value, so it still look like a 2D image. And you can take a look in this example about the this is the result of the layered neural atlas, and this is the CODEF. And more specifically, this is the canonical image from atlas, and this is the canonical image from the this is the CODEF approach. They do not have described, survey distortion effect, and also in the reconstruct video, they can reconstruct the kind of subtle motion of blinking eyes, but in the atlas approach, they cannot. And more specifically, one thing to know is that because CODEF decomposed the video editing problem into editing this 2D canonical image and then use the basically learn the deformation field over time. So any algorithm or editing algorithm for the 2D image can be applied here for editing video, right? Because we only use 2D image editing method to edit the canonical image, and it can be propagated to the whole video. So that's why it's called or claim that they can lift in the image algorithms to video. So for example, if you have a image control net for video translation, then you can apply it on the canonical image. And also furthermore, they can even do super resolution on the canonical image, and also even do some kind of like SAM segment anything to obtain the semantic mask, on the 2D canonical image and then propagate it into other video frames. And here is their result of editing canonical image with control net actually, and then propagate it to video using the learn deformation field. So CODEF is great, but the canonical image used in CODEF is, is still 2D image. And we are talking about 3D aware. Once we have a good understanding of how actually this 3D world looks like, then perhaps the video generation problem becomes less challenging in the sense of that we're just kind of like moving the camera in this 3D world. So an interesting problem we expect to dig into is that can we really represent the video in a truly 3D space? So in our recent work that we proposed the so-called dynamic video E, in the sense of that instead of editing the 2D canonical image, we wanted to edit canonical 3D nerve. And here is some quick showcase of the result. Like given the input original video, that user provide reference for the background style and the subject we wanted to customize, then this is our generated result. You can see the consistency of the motion, the movement, trajectory are pretty well preserved in the edited video. And it's much better than the previous method. And there are also another example of like changing to this kind of like background style and subject. So this is actually the first time we introduced dynamic nerve as an innovative video representation for human-centric video editing. So 3D also is a challenging problem. So there, we wanted to do this video editing based on 3D representation. Only in this scenario that we can actually obtain a very good 3D representation, and which is the actually human-centric scenario that people have a lot of data for training to actually reconstruct the 3D or 3D human scene pretty well. And this work of like representing the 3D worlds into actually nerve is from actually our previous work in ICCV 2023, so-called horse nerve, dynamic human object scene neural radiance field from a single video. So given a single video, we can try to optimize actually 3 nerves. So the first nerve is about background, background, and there are another 2 nerve or MLPs. So the idea is that we have a canonical space. We have a canonical space only for the foreground, but it's really actually 2D space. I mean, really 3D space, and it's characteristic by represented by nerve. And also we have this kind of motion, basically the deformation field that tells us how you would be able to transfer the pixel in the canonical space to according to some motion to another specific time frame. So this is from the horse nerve walls that we decompose the video, this single video in this nerve for background static scene, and also actually the motion deformation fields and the canonical human nerve. So once this has been done, basically all this are based on the horse nerve, and then we are thinking about how we can do editing based on such very good representation. And of course, since this has been decomposed, then we do this editing separately for the background and human separately. So for background, if we, for example, we wanted to make it into this kind of style, then we can first randomly render a view, and then we use this like so-called FM loss to minimize basically the distance between these 2 figures. So use that to kind of like provide a signal for optimizing the nerve to make sure they are similar in some sense, that is to minimize actually the nearest neighbor in the feature map between these 2 feature maps. And after this like training of this nerve, so note that this is training this nerve, and this would how the image finally look like. So we sort of like distill the, extract the, or inject the style from this image into the 3D representation. And for the human part, because we are only thinking about changing the subject to customize the subject, then the motion, the movement, they should be preserved. So it's fixed, it's preserved. It's fixed. Motion deformation field is fixed, but we try to learn the trying to optimize to update the nerve representation for the human. And we actually use multiple losses. So the first loss is the reconstruction loss of these 2 images of the same frontal view. And then there are also the so-called SDS loss, which is essentially trying to use the diffusion model. Diffusion model are so powerful and can produce the reasonable results, but they are not actually maybe actually tied with this specific scenario of this input single video we have. But we can try to use that to provide us with kind of like some supervision of how this image is likely to be generated by this diffusion model. And this is the idea of the SDS. And we can use some of these models, or they call prior information from 2D spatial diffusion prior. And also we can also use some 3D priors as well from this 3D 0, 1, 2, 3 model. So use that, we can train to use this couple of losses, we can train this human nerve model. And essentially, these two strings are optimized separately. And we ask, we compare it to different previous method, ask human annotators to pick the one they prefer. And we can see our method outperforms the previous method significantly, like 90% something compared to the previous method. And this column is about, so the first column is about texture faithfulness. Second one is consistency over time and overall quality as well. Here are some visual comparisons of the input video. This is our result. And this some other methods. And you can see this is another example, input video, our result. Previous method result, like in this one, they cannot really edit the person according to the subject we wanted to customize. And for some of the atlas-based approach, in such complicated scenarios, they would actually find it difficult to even form correct 2D atlas. So the editing completely fails. And maybe one extra bonus, because we are doing this editing in the 3D world, is that we can essentially enable the free viewpoints rendering. So you can view the subject, post the video at any time, view the subject from any directions. So that's pretty much what we have for the 3 aware video editing. And you can see it allows even better temporal consistency. And the very last pieces that I like to talk about is about other kind of like guidance, other signals. And there are a couple of works in this as well, and they're very interesting. So the first one I'd like to bring up to your attention is that this actually image work, instruct pixel to pixel. So the idea or the optimization they made is that, now when we talk about text to video generation or text to image generation, we typically we would like to have a editable caption, for example, a photo of a girl riding a dragon, and the original image would like maybe a photo of a girl riding a house, and we wanted it to edit it to be riding a dragon. And in order to make that happen, what we need to do or need to have for the caption is actually this description, photo of a girl riding a dragon. But you can see it's not kind of like we could have better forms in the real world user interaction, right? Because people typically would ask, hey, when human and AI communicate, they would have instruction like have her ride a dragon, and then we hope the model would be able to automatically come up with this edited caption, photo of our girl riding a dragon, something. And there could be also other instructions that convert to break, color the colors pink, etc. So instead of describing the edited video or edited image, we as users sometimes would like to directly have this kind of like short brief instructions. So this kind of instruct pixel to pixel model basically are trained to design to dealing with such instruction-based, instruction-guided image editing. So as you can imagine, for video editing, we also have some counterparts, and people in this paper instruct video to video, controllable video editing with natural language instructions. They provide this instruction and videos pairs generated by, they have this data set generated by ChatGPT, Bleep, and also turn a video. And then they train inflated stable diffusion for instruction-guided video editing. So another scenario or another guidance we have is audio or speech. So for this one, for this example, they are trying to, given the new audio utterance, new audio feature, they wanted to edit the current, like basically how the person's mouth moves. So given the previous edited frames and the current frame, we mask out actually the mouse region. And now the diffusion model is supposed to basically denoise or fill in this mask region based on the audio features, the new audio features. And also they have another condition, which is the identity frame. So you know roughly how the part looks like. And that's for speech, and they're more specifically also sound, general sound audio, like this is using the sound of the wind for guiding how the video should be edited. There are also other great works using exploring different kind of like guidance. All right, so actually that's pretty much all I have for you for video generation and video editing. And let's do a very quick summary. So for video generation, we started with some of the pioneering work like VDM and actually different video diffusion foundation models from different companies. And then we talk about open source based models, and then also some of the closed source based models. And actually, you may notice we have some update here, like with WALT, Gentron, etc. So the field is progressing so fast. As we are recording the tutorial, these new approaches, new papers pop up. Then these two are some of the diffusion models that actually based on transformers. And later on, when we have time, we hope maybe we can also do some dedicated tutorial for these new works come up. And there are also the categories that training efficient technologies like animated diff or even some training free approaches. And then when we think about more complicated scenario, like generally like movie-like videos or maybe long videos, then we cover topics like using the storyboard for video generation, and also the approaches for long video generation. And finally, we talk about this topic of like using a combination of different modalities for video generation, including maybe sound and motions, and even maybe MRIs. And for video editing, we start with some approaches that request you to train on either the video to be edited, or maybe a set of reference video in the motion director. And there are also approaches that does not require training or fine tuning at all. And later on, we spend quite a lot of time on this big topic of control editing, using essentially different kind of controls, using depth or using pose or using point, or maybe like control net. There are even also different versions of control nets, combining different kind of like conditions for control. And then after that, we introduced 3D aware. Basically, we wanted to have a canonical representation so that the editing happens in the canonical space and such editing can be well propagated to other frames across time. So that can be another alternative approach, or actually made explicit approach for enforcing the temporal consistency over time. And finally, we briefly touch on the other guidance. And we have this GitHub repository of awesome papers about video diffusion models. And we are keep updating it with the latest papers. So feel free to let us know if you found some papers not included. You can submit a pull request. Thank you for that. All right, so actually that's all I have for you. I hope you have enjoyed it. Due to the short time limit, we likely missed out some important works. Sorry for that, and feel free to comment in below to let us know. And maybe if you want, you can include some explanations about the papers. That would be very much appreciated. And also, I know this tutorial could be improved in many aspects. If you have any suggestions, feel free to comment in below to let us know as well. Thank you so much. I hope to see you very soon.